Is it visible?
Yeah, it's visible. Yeah.
Okay.
Yeah, probably we can start now.
Yes.
Our next speaker is from IISc again. So it is Aakanksha Jain. She will talk about transformation formula for the reduced Bergman kernel. Another topic, another talk in several complex variables. Aakanksha.
Yes, thank you, sir. Good morning, everyone. So the topic of my presentation today is transformation formula for the reduced Bergman kernel. This is joint work with Sahil, Gehlawat and Amardeep Sarkar. So I'll move to the overview of today's presentation. Yes, so first we will go through the definitions of reduced Bergman kernel and weighted reduced Bergman kernel, and then we will recall holomorphic correspondences, and then we will state the transformation formula for the reduced Bergman kernels under proper holomorphic correspondences. We will see a sketch of the proof also. And then we will see that if we restrict ourselves to proper holomorphic maps, then even more is true. That is, we have the transformation formula for the weighted reduced Bergman kernels. Finally, we will see an application of our transformation formula. This work is in fact motivated by Bell's work on the transformation formula for the Bergman kernels and its applications. In fact, reduced Bergman kernel is related to the Bergman kernels. And if one is familiar with Bergman kernels, then you'll be able to identify that it is in fact reduced Bergman space is in fact a subspace of the Bergman space. Okay, so now I'll move to the definition of reduced. Yeah, so before starting, I'll say that we are going to restrict ourselves to the planar domains in this presentation. Okay, so let D be a planar domain. So we define a space denoted by script D of T, the space of all the holomorphic functions f on D, such that f is an antiderivative on D and f is square integrable with respect to area limit measure on D. So we call this space the reduced Bergman space of D. It can be it can be checked that it is in fact a Hilbert space with respect to the inner product f comma g equals integral over D of fg conjugate. Also, for every zeta in D, the evaluation functional f going to f of zeta is continuous. So now it in fact follows from the Rees representation theorem that for every zeta, where we have a function k tilde d dot comma zeta in the reduced Bergman space, such that f of zeta equals f of zeta equals inner product f with k tilde d dot comma zeta for every f coming from the reduced Bergman space. So we see that we have a function of two variables here, k tilde d on denoted by k tilde d on d cross d. So such that if I fix the second variable, then this is in fact a function in the reduced Bergman space, and this kernel, so this function reproduces the entire Hilbert space. So this function k tilde d is called the reduced Bergman kernel of D. Sorry, this is a typo here. Yeah, so the function is called the reduced Bergman kernel of D. And yeah, so it is an easy exercise that the function k tilde d is conjugate symmetric. So now observe that with respect to first variable, it is a holomorphic function because it belongs to the reduced Bergman space. So because of this conjugate symmetric property, it follows that it is in fact anti-holomorphic in the second variable. So, so now coming to the weighted reduced Bergman kernel. So for that, we let mu be a positive function on D such that 1 by mu is an L infinity log of D. We define d mu of D, the space of all holomorphic functions f, such that f is an antiderivative on D and f is square integrable with respect to the weighted. This is Lebesgue square integrable with respect to this weight mu here, right? So we call this space d mu d, the reduced Bergman space of D with respect to the weight mu. Again, it can be shown that it is a Hilbert space with respect to the inner product f comma g given by integral over d f g conjugate mu of z d of z, where this is Lebesgue area measure. So and also for every zeta in t, the evaluation functional f going to f of zeta is continuous. So before going forward, I'll mention here that so for any weight we can of course define this space, the reduced Bergman space, with respect to that weight. So we have put here some extra conditions on weight, and this will ensure that this reduced Bergman space, weighted reduced Bergman space, is a Hilbert space with respect to the given inner product, and this evaluation functional is continuous. But there is in fact an even larger class of weights for which these two properties will hold. The reason I have put this condition here is because in our theorem for the transformation formula for the weighted reduced Bergman kernels, we require this condition. So this is a sufficient condition for the transformation formula to hold. So that's why I've put this condition here in the definition. Okay, so coming back to the weighted reduced Bergman space. So yeah, so now again it follows from the Rees representation theorem. So we have a function k tilde, a unique function k tilde d mu on d cross d, such that if I fix the second variable, it is an element of the weighted reduced Bergman space of d, and f of zeta equals inner product f with k tilde d comma mu dot comma zeta for every f in the weighted reduced Bergman space of D and zeta in D. This function k tilde d mu is called the reduced Bergman kernel of D with respect to the weight mu. Again, this is conjugate symmetric, and from it will follow that it is holomorphic. Since it is holomorphic in the first variable, it is anti-holomorphic in the second variable. So now we'll recall proper holomorphic correspondences. So for that, let D1 and D2 be domains in C, and pi1 and pi2 are the pi1 from D1 cross D2 to D1, and pi2 from D1 cross D2 to D2. These are canonical projections. So pi1 is pi1 is the projection onto the first coordinate, and pi2 is the projection onto the second coordinate. And let V be an analytic subvariety of D1 cross D2. So now corresponding to this analytic subvariety, we can define a multivalued map from D1 to D2, which in fact maps every Z in D1 to a set of all those W such that Z comma W is in V. We are denoting this set by pi2 pi1 inverse of Z. So similarly, we can similarly we can define a set pi1 pi2 inverse of W for every W in D2, which will be the set of all those Z such that Z comma W belongs to the analytic subvariety. So this map is in fact, this multivalued map is called a proper holomorphic correspondence, and this V is called the graph of F. And we say that the correspondence is proper if these projection maps pi1 and pi2, the pi1 is the projection from the analytic subvariety onto the first coordinate, and pi2 is the projection from maps are proper. So in that case, we say that correspondence is proper. So as an example, we can, so we have D1 and D2 domains in C. We can take the set of all those Z and W in D1 cross D2 such that Z to the power M equals W to the power N for positive integers M and N. So this is an example of, so this I've given here the graph, an analytic subvariety of D1 cross D2. So this will give us a proper holomorphic correspondence here. Okay, so few properties first. Note that there exist analytic subvarieties V1 and V2 of D1 and D2 respectively, and positive integers M and N, such that pi1 pi2 inverse is locally given by M holomorphic maps on D2 minus V2 And we will denote these local holomorphic maps by capital Fi's, and pi 2 pi 1 inverse is locally given by n-holomorphic maps on d1 minus v1, which we will denote by small fi's, I equals 1 to n. Also here v1, v2 will be discrete subsets of d1 and d2 respectively. Now note that the case when n equals 1 here, this is in fact a proper holomorphic map with multiplicity m, and these capital Fi's will denote the local inverses of small f. And of course, these are defined outside our discrete subset of our codomain, which that discrete subset are in fact the critical values of f. So right. Okay, so now we'll mention. So now we are ready to state the transformation formula for the weighted reduced Bergman kernels under proper holomorphic correspondences. I'll state it now. Let D1 and D2 be the bounded domains in C, and F is a proper holomorphic correspondence. Then the reduced Bergman kernels Kj tildes associated with the domains Tj's transform according to the rule, which is summation I equals 1 to n fi prime of z times k2 tilde of fi of z comma w equals summation j equals 1 to n k1 tilde of z comma fj of w times fj prime of w conjugate. So this holds for all z in d1 and w in d2, where small fi is in capital Fj's and the positive integers m and n are as given in the definition. Yes, so yeah, as I mentioned before, if n equals 1 here, this will be a proper holomorphic map, and therefore as a corollary, we'll get a transformation formula for the proper holomorphic maps. That is, if f is a proper holomorphic map, then we have this f prime z times k2 tilde f of z comma w equals summation j equals 1 to m k1 tilde z comma fj of w times conjugate of fj prime of w. Here, yeah, m is the multiplicity of m and capital Fj's are local inverses of f. Okay, so now I'll present a sketch of this proof. So there are many steps in the proof. I'll just mention the steps and I'll be explaining only the final step a little bit. So first for u in L2D2 and v in L2D1, we define maps gamma 1 and gamma 2 by, so gamma 1 of u is summation I equals 1 to n fi prime times u composed with fi, and gamma 2 of v is summation j equals 1 to n fj prime times v composed with fj. So first we show that for every u in L2D2 and v in L2D1, so for every u in L2D2, gamma 1 of u is in L2D1, and for every v in L2D1, gamma 2 of v is in L2D2. So these are well-defined maps between the correspondence L2 spaces, and in fact these are bounded linear maps. And next we show that for every u in L2D2 and v in L2D1, inner product of gamma 1 u with v is same as inner product of u with gamma 2 of v. And next we show that the image of the reduced Bergman space of D2 under gamma 1 is contained in reduced Bergman space of D1, and a similar statement is true for gamma 2, that is the image of reduced Bergman space of D1 under gamma 2 is contained in the reduced Bergman space of D2. So we see that if we restrict our maps gamma 1 and gamma 2 to our reduced Bergman spaces, we have bounded linear maps between which we will denote by gamma 1 tilde and gamma 2 tilde between the corresponding reduced Bergman spaces. Also, we have this property which is given in the bullet point 4, that is gamma 1 tilde u. The inner product of gamma 1 tilde u with v is same as the inner product of u with gamma 2 tilde of v for every u in the reduced Bergman space of D2 and v in reduced Bergman space of D1. So in the final step, so what we do here, for every w in D2 minus v2, we define this function g of z equals summation j equals 1 to n k1 tilde z comma fj of w times conjugate of fj prime of w. So where Z is coming from D1. So we see this is a well-defined function, and here W is fixed. So the second variable is fixed. So we see this K1 tilde as with respect to first variable, they in fact belong to the reduced Bergman space of D1. So this is in fact a linear combination of some of the elements which are coming from the reduced Bergman space of D1. So this G is an element of script D of D1. Now, for an arbitrarily chosen V in D of D1, consider the inner product of V with G1. So this Fj prime of W will come outside, and we'll get summation J equals 1 to n Fj prime of W times inner product V with K1 tilde dot comma Fj of W. So by the reproducing property of K1 tilde, this inner product is in fact V of Fj of W. This expression is in fact nothing but gamma 2 tilde of V computed at W. Again, by the reproducing property of K2 tilde, this is in fact the inner product of gamma 2 tilde of V with K2 tilde dot comma W. Now this is equal to inner product of V with gamma 1 tilde of K2 tilde dot comma W. So this comes from this property, which right. Okay. So, right. We have shown that inner product of V with G equals inner product of V with gamma 1 of K2 tilde dot comma W for every V in script D of D1, which implies that G is in fact gamma 1 of K2 tilde dot comma W. So if we write the expression for gamma 1, this will give us that summation I equals 1 to n. So this is in fact the transformation rule which was mentioned in the statement of the theorem, but this we have proved for Z in D1 and W in D2 minus V2. But observe that LHS is anti-holomorphic in W, left hand side, and V2 is a discrete subset. So it implies that so V2, all the points in V2 are in fact removable singularities for right hand side. So this rule in this formula holds everywhere by continuity argument. So this completes the sketch of the proof of the transformation formula. Now, if we restrict ourselves to the proper holomorphic maps, the more is true, that is, we have a transformation formula for the weighted reduced Bergman kernel. I'll mention it now. So we have D1, D2 bounded domains in C, and nu is a positive measurable function on D2, such that 1 by nu is an L infinity log of D2. So if F is a proper holomorphic map from D1 to D2, then the weighted reduced Bergman kernels K1 tilde nu composed with F and K2 tilde nu. So the weight is also transforming according to the map. So these kernels associated with D1 and D2 transform according to the rule F prime Z times K2 tilde nu of F of Z comma W equals summation K equals 1 to n K1 tilde nu composed with F of Z comma Fk of W times conjugate of Fk prime of W for all Z in D1 and W in D2, where M is the multiplicity of F and Fk's are the local inverses of F. So I'll not give any idea of the proof here. So the proof techniques are similar. Of course, this is different because there is this weight involved here, and there is a reason of taking this condition on the weight, but I'll not go into that. Instead, I'll move to the application of the transformation formula. So, so the theorem says that if D is a bounded domain in C whose associated reduced Bergman kernel is a rational function, then every proper holomorphic mapping F from D to the unit disk must be rational. So in order to prove this, we need a lemma due to Bell. So before that, let us fix some notations. So we will denote the reduced Bergman kernel of the unit disk and the domain D by capital K and capital K tilde respectively. And so we first for a fixed W in the unit disk and alpha non-negative integer, we define a linear functional lambda on the Bergman space. So Bergman space is the space of all those holomorphic functions which are square integrable on D. Yeah, so we define a linear function on the Bergman space by as follows. So here, for every h in A to D2, sorry, for every h in A to D, lambda of h equals. So here, this, if we assume that this is the function, so summation k equals 1 to n fk prime times h composed with fk, if this is the function of, let's say, z, then I'm differentiating it with respect to z alpha times, and I'm evaluating it at this fixed point w. So this is my linear functional. So now the lemma due to Bell is related is on this linear functional lambda. It says that so if zeta, xi1, xi2, and so on, xiq are the points in the inverse image of w under f, then there exists a positive integer s and constants cl beta such that lambda of h is given by summation L equals 1 to q, summation beta less than equal to s, cl beta times beta's derivative of h computed at zeta L. So this holds for every h in A to D. So yeah, we are going to use this lemma. So coming to the proof of the theorem. So assume that the inverse image of f inverse, sorry, the inverse image of 0 under f is this set given by zeta 1, zeta 2, and so on, zeta q. Now this linear functional lambda was corresponding to a fixed point w in the unit disk and a non-negative integer alpha. So I'm taking a linear functional on A to D, that is the Bergman space, corresponding to alpha equals 1 and the point 0 and D. So the above lemma, so yeah, to write it explicitly, this lambda of h is in fact del by del w of summation k equals 1 to m fk prime h composed with fk, and this is being computed at 0. So the lemma now gives that this lambda h, this here, so lemma gives that we have a positive integer s and constant cl beta such that, so this is in fact our left hand side is lambda of h. So this is summation L equals 1 to q, summation beta less than equal to s, cl beta times del beta h at computed at zeta L for all h in A to D. So now we have a transformation formula for the reduced Bergman kernels under the proper holomorphic map. If we differentiate it with respect to w conjugate and set w equals 0, we will get this first equality, which, so that is f prime z times del by del w conjugate of k of f of z comma 0, which equals this. I'm not reading it out. I'll just say that now after this, so of course there are some computations involved here. So after this, we'll apply this lemma. So here this lemma is being applied for, so here in place of h, the function which is being taken is k tilde dot comma, sorry, the function which is being taken here is the conjugate of k tilde z comma dot, right? Oh, okay. So yes, so here observe that we are given in the hypothesis that k tilde is a rational function. So here the right hand side is a rational function. Therefore, this left hand side is a rational function in z. So we have shown that f prime z times del by del w conjugate k of f of z comma 0 is a rational function in z. Similarly, if I start with a linear functional corresponding to alpha equals 0 and this point 0 in the unit disk, then I'll get at f prime z times k of f of z comma 0 is the rational function in z. So therefore, the ratio of these two terms is a rational function. Now, when we talk about the disk, the reduced Bergman kernel is same as the Bergman kernel, because this is simply connected every holomorphic function as an antiderivative. So we can now we have an explicit expression of the Bergman kernel, and hence the reduced Bergman kernel for the unit disk. So we can compute these derivatives of k, and then from it will follow that the ratio of these two terms, f prime z times del by del w bar k of f of z comma 0 and f prime of z times k of f of z comma 0, it is in fact 2 times f of z. So since both numerator and denominator are rational functions, this is a rational function, and therefore f is a rational function. So this completes the proof of the application. So like, okay, so yeah, I'll end my presentation here. Thank you.
Yeah, thank you very much. Are there some questions?
Could I ask a question?
Yeah.
Aakanksha, hi, this is Gautam.
Hi, sir.
Could we have...
Sure, sir. This one?
Okay, maybe the second one, yeah. So I thought I had understood, and then at almost in the last 5 minutes, I got confused about something. I'm trying to understand the elements that belong to script D of D. So you said that these are functions. You are saying the elements are the functions f, and each function f is the g dash of some element in that is already holomorphic in D.
Yes, yes.
So you use the word antiderivative. You probably mean derivative, right? Every function arises as a derivative of,
yeah.
right? Yeah.
Yes.
Of course, for the disk case, as you said, the Bergman spaces do coincide, whether you say anti or not. But are the elements, so is line number 3 on the slide a typo? The elements are antiderivatives, or the elements are derivatives of some holomorphic function?
So
if you look at the third line from the top, you say that elements are equal to g dash for some g.
Yes, so yeah, right. As you said, f is the derivative of some holomorphic function on D. This is correct.
Maybe so, not antiderivatives, but derivatives. So condition for belongingness is number 1, these are derivatives of some holomorphic function, plus the element is L2 integrable, yes?
Right.
Okay. And then I was also wondering, so I think this probably is the answer to my question, but are your results just for planar domains, or for the purposes of this talk, you are focusing on planar domains?
No, the results are for planar domain. So here we have this condition. So in fact, this is a subspace of the Bergman space where we don't have this first condition.
That's
but,
right.
Yes. So the thing is, when we, so let's not talk about the weighted case. Here we don't have, in the higher dimensions, we don't have something analogous to this first bullet point.
Correct.
For which this will become a Hilbert space and the evaluation functional is continuous. We have tried it, but we haven't found it anything yet.
Okay.
So yes, so
I suspected as much. Yeah. So there's like right from the start, because if you try to write down an analog, then already you would be, if you had more than one variable, you'd be forced to look at the, consider this in the family of, in the language of forms, for instance, right?
Yes, right. We were looking at something of this thing. We tried a lot of definitions, but
very interesting. Yeah, but but it'll be interesting to keep thinking. I mean, there might still be some object in some vector valued Bergman space, maybe.
Yes.
Right. Thank you.
Okay. Yeah.
Now, if I have a question, I mean, maybe a comment. If you think of this thing, some kind of Sobolev spaces, you want the derivative to be in a weighted Bergman space, but your starting point G is only holomorphic. So what happens if I start with a weighted Bergman space, take a G from a weighted Bergman space, but G hat also has to be in the same weighted Bergman space? Do you get something different?
Okay, so you are saying that
your definition, instead of taking G to be any holomorphic function on D, Suppose I want G to be in the weighted Bergman space, but G prime also has to be in the weighted Bergman space.
Okay, so both are
Yeah, in the same weighted
in the
Bergman.
weighted Bergman space. I think we'll get the answer is not the same. We'll get something different. Yeah.
That's not interesting.
We'll have to look at it, because it will be interesting if it has some nice properties, just like it has. So it is a Hilbert space with respect to them. We'll have to look at it.
No, that will be a Hilbert space, but then the problem is whether
if the evaluation functional is continuous or not, all those things. Yeah, and which this question is also that which evaluation functionals to consider, which will be interesting. So here, right? Okay. So as you said, as you said, if we consider both F and G in the reduced Bergman space, so in the weighted Bergman space, weighted reduced Bergman space, then maybe we can also talk about the evaluation functional F going to F prime of zeta. So yes, we don't know, we have to check it.
Okay.
Maybe I want to add a comment here to Thangavelu's question, that what you're saying, I think, has been done for Hardy. So you there's this thing called Dirichlet space, where you take functions in the Hardy space whose derivative is in the Bergman space.
Yeah, so
sort of a Hardy-Sobolev spaces kind of things.
That's what you started. Yeah, right, exactly. But I don't know this. Yeah, I have not seen this for being done for Bergman.
In fact, Sakai has considered some kernels where he has higher order kernels also, but so corresponding to n equals 1 there. This is, I mean, what he does is he takes here I have taken all those functions for which such that F is G prime for some G holomorphic and it is L2 integrable. He takes in the space, he takes all those G here. So this is the difference. So we can in fact, this is in fact an equivalent way of stating that.
So I have a question. Aakanksha, can you hear me?
Yes.
So here you mentioned that this weighted Bergman space is RKHS even for larger class. So what is that condition?
Those weights are called admissible weights. So Pasternak, Wieniawski introduced this term admissible weights for the Bergman spaces. He defined admissible weights like this. So all those weights for which, obviously for any weight we can define this notion of weighted Bergman space, right?
Yes.
But whether it is a Hilbert space, that is a closed subspace of L2 space, or whether the linear functional is continuous, we don't know. So he defined so he said that a weight is an admissible weight if these two conditions are satisfied. Then he gave a lot of conditions on the weights for which it will be an admissible weight. I don't know if there is both a necessary and sufficient condition, but there are a lot of sufficient conditions which will ensure that a weight is an admissible weight. So for all those admissible weights, this thing works. Condition on the weight. In fact, if 1 by mu to the power a is locally integrable on D, it will imply that it is an admissible weight for some A positive.
I see. Okay, and could you go to definition of holomorphic correspondence?
Sure.
So so here you define this proper holomorphic correspondences. So I think like it seems like for proper holomorphic correspondences, we can give some necessary and sufficient condition on this subvariety phi. Proper something like that. Can we do that? Like in terms of dimension maybe, or something like that.
So you are saying some conditions on the dimension
of on that variety, so that it will be proper or something like that.
I don't know. So I don't know the answer right now, but because I haven't thought about it. Yeah.
Thank you.
I have a quick question. Is it okay?
Yes, sir.
So can you show that theorem you had about when the kernel is a rational function or something like that?
This one. Yeah.
I see. So, most of this, are some of these domains also simply connected?
No. So here D is any bounded domain in C.
Yes.
Yes. And so whose reduced Bergman kernel is a rational function? In fact, yeah, there is this analogous result, not exactly analogous. In fact, for Bergman kernel, even in higher dimension, we have a result of this, something of this sort. But if we restrict ourselves to planar domains, since you were talking about simply connected domains, the Bergman kernel is rational if and only if it is simply connected, if and only if the domain is simply connected. But so yeah, this will be beneficial if we get a domain, which is of course not simply connected, for which the reduced Bergman kernel is rational. So we don't know whether there exists such domain or not.
Oh, for the actual Bergman kernel, you are saying that it's rational if and only if it's simply connected.
Yes, yes.
Oh,
But yeah, so it will be helpful if we get some bounded domain for which the reduced Bergman kernel is rational, but the Bergman kernel is not rational, but we don't know.
I see. You don't have such an example. Is what
Yeah,
you're
right now we don't have.
Okay.
Yes.
Thank you. Thank you.
So I had one very quick comment.
Yes.
So this was in connection with something Mayuresh mentioned. So when you use the word multi-valued maps in the context of correspondences, you are probably thinking about something like the graph of the square root function or some such thing, right?
Yes. Yeah. So in the example also, I
Yes.
took some kind of
Right.
that kind of
Yes.
example
Yeah.
only.
I do think that, in fact, so, Mayuresh was talking about restating and then carrying out this whole project in terms of an analytic subvariety of the product domain, where you start with the condition of analytic subvariety, you take the dimension to be the dimension of whatever is the common dimension of D1 and D2. So rather than limiting to multi-valued maps, simply going with subvarieties of the product domain, where the dimension is the same as the dimension of the product domain, and demanding that the projection maps are proper. So I think I know there is a result in Chirka's book, which will then give us examples of V which are much more complex than, much more sophisticated than this example. And I think all of your machinery will go through. I mean, of course, the last result is for maps. What I mean is the machinery and the result for the transformation formula, it will actually go through comfortably. It'll be uglier. The individual steps will be uglier, but it will go through.
Okay. Yeah. Yeah. We'll go through it. Doing directly with working with analytic subvarieties.
Yeah. So the dimension has to be. I mean, it's sort of a necessary condition for properness, obviously, and I think that is what Mayuresh was referring to.
Okay. Okay. Yeah.
I think it's time for the next talk. Let's thank Aakanksha once again, and then we'll move to the next speaker.